Hello everyone, what is up? I hope each one of you is doing very well at your homes. And today we are back with another banger of a video on a topic called Transformers. It isn't a big topic, but a decently difficult one. I won't call it hard because that would be a disgrace on other hard topics. But yeah, a very essential topic. Which comes under the vast part of your electromagnetic induction. So the thing is, we won't be going into too much detail of Faraday's law and everything. Otherwise, we'll lose the essence of what we are studying today, right? So without further ado, let's directly jump into it. So we'll start by defining transformers, right? What are transformers? So basically, right now I want you to imagine the road trip where you're going on a road trip playing Punjabi songs with your family, and then when you look out at the window seeing views, you see these huge Eiffel Tower like structures, and then in the middle there are boxes placed, right? So, what are those? Those are basically transformers, and today we are going to study about them. So how do you define it in English language or science, whatever you want to call it? So transformers are basically a static device, static electrical devices which use alternating current to change voltages or currents without changing frequency, and it is mainly used to convert voltages to high or low, right? Static electrical devices which use, let's just not write use because that can change the meaning, which can change uh, voltage or current without changing frequency, right? So this is the basic English definition of transformers. So if it comes in exam, you have to write these exact words, right? And you can use for revision as well. So this was the English definition. Now we switch to how it looks, right? So now we switch to how it looks. So how does it look? So this basically iron. I know I wanted you guys to imagine that Eiffel level structures, but obviously those are a part of transformers, but they are extensions. The basic transformer will look like this. So this is, I'll tell you what this is, right? Let me first just draw it. So right, ignore the accuracy of the diagram, but still, this is what a transformer in essence looks like. So I'll tell you what this is, right? I'll tell you what this is. Let me just fix it a little bit, and then we can all be set. Right, so I fixed it now. So this is what a transformer in essence will look like. Now we'll start labeling it. So this is basically made up of a soft iron, and this is the core of a transformer. So this is soft iron core, right? This is the primary coil. We'll call it PC in subscript, and this is the secondary coil. We'll call it SC in subscript. And this is the input, and this is the output circuit, and then there are extensions with that Eiffel Tower like structure. So now I'll come to explanations. So why is the coil the core only made of soft iron? It is because you'll realize that in electromagnetic induction, how easily a substance can be magnetized, that matters a lot. And soft iron is one of the metals which can be most easily magnetized. So without any too much effort by the magnetic field or by humans, this can get magnetized, and that is exactly what we need in an equipment like a transformer, right? So that is why it is made up of soft iron. And then we have the primary coil and secondary coil, which are made of copper, because obviously because of its ductility and conductivity. And then there's the input circuit and output circuit. So now in the input circuit, you'll always see alternating current, right? So alternating current is always supplied through the input into the primary coil. Uh, right. So why always alternating current? We'll come to that. Wait a minute. Let me first show you what happens, right? And then we'll come to basic questions. So when this alternating current enters the primary coil, if you have studied a solenoid or basic electromagnetic induction before, you'll know that when a current flows through a coil of copper or any conductive substance, it forms a magnetic field, something like a magnet when north and south poles attract. So basically like that. So it forms a magnetic field, something like this. This is when a current flows into the page, but we don't flow the current into page here. This is a different story, right? So then what happens when the current flows in primary coil? There's it creates a magnetic field around it. The magnetic field is not round here. It can be round, but for accuracy, because it is in the soft iron core, right? It is in the soft iron core. That is where it is. And this is the magnetic field. This is the magnetic field, right? So when this magnetic field is cut by the secondary coil, right? So when it is cut by the secondary coil, it induces an EMF in it. What is an EMF? Electromotive force. I'm sure would have studied if you have clicked on a video called Transformers. I'm sure you'll have studied basic electromagnetic induction. So so when this magnetic field is cut by the secondary coil, it induces an EMF. Mark my words, these are very important words. Induces an EMF. And this EMF flows to the output, to the output circuit, to your homes or to power stations. We'll come to that. Don't get confused. Are you understanding my word? What happened? Let's summarize. There was an alternating current in the input voltage supplied to the primary coil. And then when it flew inside the primary coil, it created a magnetic field. And when it created a magnetic field inside the soft iron core, that induced and that is cut by the secondary coil. Cut. And when that is cut by the secondary coil, it induces an EMF inside the coil which flows to the output circuit. Right? This is the basic functioning of transformers, but it is way more than that, trust me. Two questions that could arise in a curious mind is that why only alternating current? Right? The first one. So the reason there is always an alternating current is because we need a changing magnetic flux, changing magnetic field basically. And without that, if the magnetic field is static and not changing, it won't be cut by the secondary coil. And if it won't be cut to the secondary coil, it won't induce an EMF inside the output voltage, and the whole functioning will not work if the current is DC. And that is why we only have alternating current when we are using a transformer, right? And the second question is that the second point I like to mention is that number of turns matter a lot. When I say number of turns matter a lot, this is because there are two types of transformers, right? Step up and step down. So, a step up transformer will step up the voltage and decrease the current. We'll come to that, but let me just tell you. And a step down transformer will decrease the voltage and increase the current. So that is why number of turns are most important, because if there is one coil, there is let's say one induction of EMF. If there are two coils, the EMF induction is doubled, because the same magnetic field is now cut two times. I'm sure you have studied this in electromagnetic induction, but it is always important to apply it in topics like this, right? So this was the functioning of transformers, right? I hope you have got it. Now we switch to what numericals will ask us. Numerical will ask us on the basis of two formulas. There are two formulas, right? Vp upon Vs equals Np upon Ns, and IpVp equals ISVS. Remember the subscript? Primary and secondary, right? I hope that is clear. So let me first tell you what the formula is. This is voltage in primary coil divided by voltage of secondary coil is equals to number of turns in primary coil divided by number of turns in our secondary coil. Got it? So, right. Why is this? So why is this a voltage? So because there is a single coil, according to Faraday's law, I won't go in detail. According to Faraday's law, it will induce an EMF, and if the coil is same, the magnetic flux output and input are both the same. And because the ratio of induction of EMF in both the coils are same, we have this formula. I told you why number of turns matter, right? So this is the formula that you will be using a lot when solving questions of our transformers, right? And the second equation or formula that you'll be using is IpVp equals ISVS. This happens for again the same reason of Faraday's law, that if the coil is same, then the ratio of EMF would be the same in both coils. So it happens for the same reason, that current in the primary voltage and multiplied by voltage in the primary coil is equals to the output current. So input current basically equals to output current. This is because transformer is said to be 100% efficient, though nothing is in the world is 100% efficient. It's around 98 to 99%, but it is said because that is what we visualize, and that is what theory is all about, right? I'll take a break of a second. Just give me a second, because I have to drink water too, right? Right. So I hope you got it now, that input current is equal to output current, and this ratio of voltage and current in the secondary coil is nearly the same. Now, one question that I've been facing a lot and I've been asking my teachers is that when stepping down the transformer or stepping up the transformer, why is there current in the secondary coil? I understand. I understand that there's voltage because of the thing I explained right here. Why is there a current? There shouldn't be a current, right? Seems that I was a foolish guy because I should have cleared my basics. I'm sure if you will know if you have clear basics, but the reason there is a current in the secondary coil is because what is EMF? EMF is the electromotive force which pushes charge around a circuit, right? So that push of charge, what is EMF doing? It basically pushing charge. So induction of EMF will push current through a circuit. So that is why there is a current in the secondary coil, because If there is an EMF, then there is a current. I mean, it all seems stupid at once, but it is what physics is, right? Physics makes you go crazy at a point, right? So that is why there is a current in the secondary coil. Now we switch to a little hard part. Application of transformers comes, right? So this is a power station. Imagine power station. So this is power station, and then these are those Eiffel Tower structures. Transformers, transformer. Ignore my diagram skills, guys. It's not good at the board. It's decent at the paper. Though. These are transformers. And then this is your house. Got the same old house since nursery, but yeah, right. So this is the power station. This is the input, and then this is the output. You see that a lot during road trips, right? This is the visual that we are growing up, and then we have seen it since we have came into this world. This is the normal visual of a road trip in India and everywhere, I think. So this is the power station. Coming back to the topic, power station. Now power station supplies energy and voltage in huge amounts because it can't at similar amounts. It merely has to give power to the whole area or the whole village, right? So when power stations gives an input in the form of AC, these are transformers which are what? Step up transformers. These right here is a step up transformer. Not talking about third one. This, when initially power station has to transfer it through power cables, this is a step up transformer. So what a step up transformer does is that it will step up the voltage and step down the current. Why and what, right? Why and what? Here's what we'll know. So if you have done physics and you have done electricity, there are two equations you will also know. P equals IV and P equals I square R. P equals I square R. P equals IV will tell us. P equals IV will tell us that when you are talking about power and this kind of stuff, not the Ohm's law, this is a different thing. When you are talking about power and when it's constant, when voltage increases, your current will decrease. That is exactly what it tells us, right? P equals I square will tell us that this is for power laws, guys. Power laws. I hope you know that. Let me just clarify that this is the equation for power laws. I square R, current squared times R. See, right? Current squared times R, and I'll see you guys in a break.